So, you know these advertisements we have been seeing on TV about how to profile desktop applications? Well, can we turn off the lights, please? Excellent. Yeah. So, anyway, let's get started. Let me show you some bars to scale. I won't really tell you what these bars are about right now. We'll just go one by one to see, the proportions of different things. So, that's it. Come here. Come here. I'm gonna measure your head. Yeah, I'm gonna measure your head. So, Dot is a smart man. He's writing a new debugger content. He's written a bunch of XML stuff which I can really not understand. So Dot's brain is 20 centimeters long, right? I don't know how he manages to understand all of this, only 10 centimeters. But anyway. Say you're working in your computer. So you have your beautiful wooden desk, you bought it at IKEA, as everyone else. You have your computer, and you don't remember something. So you reach for a book. Like, your radius of action in your desk is generally about 80 centimeters, right? Let me take someone else. What's your name? Arti. Okay, so can I measure your arm? Okay, 80 centimeters. No, really, look. So, if you have to go out and read something on the other side of your desk, it's 80 centimeters, You'll get hurting your back if you try to stretch more than that. So that's like your working set of books, the ones that you have in your desk. If you have to go to the other end of the room, this was the cheap one, so it only goes to 3 meters. But if you have a pretty big bedroom or study room, this is 3 meters, so 4 meters should be around here. You have to stand up, walk to the other end of the room, pick the book, go back to your desk, sit down, read the book, and say, oh, okay, now I have it in my brain, so it's much faster to access. Got that? But there's another thing in the bottom. It's something that's really far away. So let's see just how far away it is. Let's scale this. That's half the original size. So they are still to scale, right? So this something is not, it's not inside your apartment. It's more than 10 meters away. So let's scale it back. It's not at the end of the hall. It's not within 25 meters either. Scaling down. This thing is it's really far away. It's not the corner store either. 1 kilometer away. You can see the little, the people with really good eyesight, unlike mine, they can barely see the orange stripe here. So what is this thing that is so far away? Are any of the open office people looking at the speed of their piece of crap so they can? Anyway, so this is we're starting to see something here. That's the university campus. Right? We are somewhere, where the hell are we? I guess we're something around there. Probably there. So, it's much farther away than that. Let's zoom out. That's a pretty good chunk of Brussels. Zooming out. That's a pretty good chunk of Belgium. Good chunk of Europe. There's a number over there, I think. So what the hell is this? If we scale back to 3,200 kilometers, right? We are, what's this, Saudi Arabia? That's Iraq over there, Persian Gulf. So what the hell is that thing that is so far away? Let's go back to the original scale. But now, instead of making it distances, let's make it nanoseconds. Something that we programmers are very familiar with. So, my machine is 3 gigahertz. right? That means that it executes one instruction every half nanosecond. So if I run an instruction in my processor and it only has to access the registers there, and if I consider that it takes half a nanosecond to access a register and to run the instruction, then we have the first bar there. This is exactly to the same scale as Dotty's brain, the desk, the room, everything. If you access something that is just in the L1 cache in the processor, which is not in the registers, but it's something that is already fetched from memory, it's really fast. It's only 2 nanoseconds. But it's still 4 times slower than a single register access. If you actually have to go to memory, because the data is not in the processor's cache, memory accesses take 10 nanoseconds these days, right? So if your program is accessing this huge array, and you end up jumping along the array, it will take 10 nanoseconds for each access instead of 0.5. So that's a factor of 20, right? So let's zoom out. To the same scale as before, we're scaling it down, That's 1 disk seek. 1 disk seek is 8 milliseconds. Every time your program has to access a file on disk and it makes the disk change the position of the hard drive head, that's 8 milliseconds. That's 6 orders of magnitude larger than accessing something in the processor register. That's 5 orders of magnitude larger than accessing something in memory. And there's nothing in between. If you do things near here, it's going to RAM, and there's nothing in between going to RAM and actually hitting the hard drive, right? So you are either really fast or really slow, and there's nothing else possible. Okay. There's this famous man, kernel hacker, desktop hacker, who once said this, as processor speeds increase, processors are getting faster all the time. And hard drives have not improved their speed for years. They barely improve their speed. So we are making our machines wait all the time for accessing the hard drive. And later, this famous man, the man who drew all the beautiful icons in GNOME, Thomas Postmanen, he wrote this on his blog a little while ago. He bought a new PowerBook, or what? No, he got a new ThinkPad, which is much, much faster than his PowerBook. A lot more memory, a lot more powerful processor, no groupy operating system like MacOS. And he feels his new machine is just about, he feels that it's about the same speed as his old machine. What's the problem there is the hard drive. So the programs in both machines are accessing the hard drive just as much, so both machines are equally slow to him. This is a very informal chart of how things have been going in terms of speed. Disks have barely improved their speed. At some point, processors overtook memory. That was like between the 386 and the 486. In the 486, they added a memory cache in the processor because the processor was now actually faster than memory access. And it's been going on since then. So there's no way our programs can be fast if we do too much disk access or too much memory access. Okay, where are we going to bother optimizing things, It certainly feels uncomfortable to use a slow program because, you say, oh, I wish my machine were faster, and, you sit there for several seconds watching programs load or watching something spin while your programs load. You end up sitting for minutes while your machine reboots. So it's really uncomfortable. Quite bother. We can just wait it out. So, has everybody seen the new version of Microsoft Office, Office 12? This beautiful, they took Office, they resigned the complete user interface to make it more usable, and this is one of their usability experts. So they actually found that in their usability tests that when people found something that was really slow, they had a lot of trouble using it. Because they said, okay, what the hell is going on here? I move my mouse and nothing happens. And a little time afterwards, something moves, actually catching up with your mouse. So they discovered that some things which are really hard to use or really uncomfortable and they are slow. As soon as the programmers start working to make them fast, they become instantly more usable without any changes to the user interface. So the other reason we want to make things fast is to dominate the world. I mean, the whole world is going to be using old PC machines pretty soon. And they're really low powered. You know, they have a slow processor, slow memory. They have no hard drive. They just use a flash card. And we're certainly...
How fast is flash in your chart there?
I don't know, probably, 100 times lower than RAM. I have no idea. But it's still like 1 order of magnitude, so 6 orders of magnitude. So there's nothing in between. Also, wouldn't you like to be able to buy a cheaper laptop rather than the 300, rather than the latest model, which is always $3,000? The laptop you want is always $3,000. Yeah. So how the hell are we going to make things faster? When people want to make their programs faster, they immediately say, okay, I'm going to make this faster. Boom, there's their big idea. But how much faster? This doesn't let you set a goal. This doesn't let you see when you're done. This doesn't let you see regressions. If you make your program really fast, over time it will get slower because you will keep adding code, modifying things, changing APIs, and eventually it will be just as slow as it was before. So how do we keep that from happening? How do we optimize a program and make sure that it ends up being fast after a number of years of changes? So the first thing you have to do is to set a goal. You have to say, I want this pop-up menu to appear in under 1/10 of a second. Once I reach that goal, I'm done. I don't need to optimize it anymore. The user is not going to perceive any difference between the menu appearing in 1/10 of a second and 100. So there's absolutely no point in going past that, right? What are other kinds of goals you have? Well, there's this guy, Phil Van Hoof, working on a new mail program, and his goal is something like, I want my mail program to use less than 10 megabytes to show a mail folder with 50,000 messages. You know, he has been working towards that goal. Or launch a program in under 1 second. OpenOffice these days takes like 8 seconds to launch in my machine, and it's like the fastest laptop I could get. That's just ridiculous. So once you set a goal, you can blame people when things go wrong again. You are done when you reach your goal. Since you have to get your timings over and over again, by that time you will have created a little benchmark to test the thing you are doing. I'm not going to let you take the picture. I'm not going to let you. So by the time you create a benchmark, you have a way that's easy to reproduce, an easy way to reproduce your measurements. And then you can use it as a regression test in the future. That's what they've been doing with Cairo. The new performance test suite for Cairo, it's a big list of performances. You know, how long it takes to draw a polygon, how long it takes to draw a gradient, how long it takes to draw a big complicated Bezier curve. And the way they do it is they record all of the sessions of their performance test suite, and they keep a history of that. So they can compare the timings of their benchmark at any 2 points in time and see, okay, something went wrong between this version and this version because now things are, 5 times slower or something. So we didn't know that a few years back. So when, Stefan Kulo in SUSE, he made a lot of work for SUSE 9.3 to improve the boot time. So boot time in SUSE 9.3 was actually pretty nice. And then it went to hell for SUSE 10.0. It went to hell because we never had a way to keep taking those timings consistently. So between SUSE 9.3 and SUSE 10, people started adding more crap to the boot process, changing the daemons, changing the startup things, and now it's just as slow as before. Right now SUSE takes, 1 minute to boot, 2 minutes to boot. So all the hard work that this person did was worthless because we didn't test it all over again. So, there's this guy who is one of the pioneers of performance stuff in general. So, let's see. Let's say how do you decide how do you decide what to start optimizing in a program? Say your program has two parts, or a little part of your process has two parts. For example, to pop up a menu, you have to create the menu, populate the menu items, load the icons for the menu items, create the corresponding widgets, and finally show the menu. And you think by intuition, okay, I think that creating all those labels takes a lot of time. So let's imagine that the menu only had two parts to it. Like it had only the labels, and only the icons and the labels. And you say, I'm going to optimize the labels because I'm really sure they are really slow. So if you had taken your timings, instead of just doing it by intuition, you would have seen that part A takes this much time, you know, and part B takes this much time. It doesn't matter if the parts are not like big, nice, contiguous chunks, right? This could be a little part here, a little part here, and a little part here, but if you spread them out, they look like that. So you work for 2 weeks, you work really, really hard to make this part faster. You make it 5 times faster, right? And everyone gets really happy when they make something 5 times faster. I mean, that's a lot. But in the end, you know, in the big picture, it's not really much faster. You know, if this took, what, 15 seconds? Well, maybe it only takes 11. And that's not a huge change. I can still go make a coffee that time. But if you had worked on making the red part twice as fast, which is not such a big improvement, this wins, you know? So before starting to optimize anything, you really have to know what the slowest part is. You cannot do it by intuition. You really have to take your measurements in the machine, and then you'll see what to optimize. There's another consequence to this. For example, let's say you need, let's say that the absolute fastest you can make each of these parts is, the fastest you can make the red part is twice as fast as before. And the fastest you could make the blue part is this little square. So if after doing this, the red part, you do the blue part, you will end up like this, right? If your goal was to get to here, there's no way you're going to be able to achieve it if this is the fastest you can go. So by setting your goals and later analyzing how much faster you can make each part, you'll actually know if you can, if you can actually reach your goals. So how do we measure things? Well, we use a profiler. Profiling tools in free software in general, they suck. gprof is completely useless. It doesn't work for shared libraries. It doesn't work for multi-threaded programs. It doesn't work for things which you use with DLOpen. So it's very nice for the examples in the gprof manual, but otherwise it's useless. Oh man, I don't have sysprof installed on my laptop. Does anyone have sysprof out there? No? Man, I wonder if the software is so slow. Okay. Well, I'll try to show you sysprof later, but I don't have it installed. Sysprof is this CPU profiler. You run sysprof, you hit the start button, you run a program, you hit the stop button, and then it will show you a tree of all the functions that got called in your program with their respective timings. So you can start seeing which functions took the most time. Sysprof, unfortunately, only shows you CPU time. If you have an application waiting for disk I/O, it won't show you that. Or you can use strace to monitor syscalls. So what's the problem with strace? Once you run strace and you give it the options to say, give me the timings for each syscall, this is the garbage that strace brings. It says, process ID, timestamp with microseconds, name of the syscall, parameters. And that's, if you are a very patient person, you can go through that log. So this is the kind of log I was getting a few months ago when I was profiling Nautilus. The startup time of Nautilus. I was trying to see why the hell Nautilus takes like 4 seconds between the time you run it and the time it actually paints the desktop for the first time. So Nautilus startup is 196,000 syscalls. You know, and it's just impossible to see what the hell is going on there. So back to Dotty's brain. Can I? So 20 centimeters by 16, well, 15. Okay, thank you. Oh, and the police. 9. You know, that's, what's that? Like 1,000 cubic centimeters of gray matter. So in your 1,000 cubic centimeters of gray matter, you have a very sophisticated computer for processing visual information, right? Your brain does not understand this crap. Your brain wants to see porn or pretty pictures or pretty graphs, you know? So you have to use your brain's capacity to understand porn instantly. You're looking at pictures and you say, I like, don't like. Like that. It's automatic. It's really, really fast. So I spent 2 hours writing a little Python program that parses that S-trace crap and draws this chart. So there's a bunch of checkpoints here, and I'm sure that people who even in the 4th row cannot see it because it's too small. But anyway, this is the chart it brings. And it says, you know, this is a timeline. It says 1 second, 2 seconds, 3 seconds, 4 seconds. And those little lines connect the, you know, the checkpoints in the program startup. So immediately you can see that here there's a big problem because all this crap is happening in a really small space. So this is, it's not worth it to optimize this because it takes, you know, 6.32, 6.38. From here to here, it takes 0.06 of a second. While between here and here, you can see that it takes, you know, almost 2.5 seconds. So there's something going on here which takes 2.5 seconds, and you say, what the fuck is that shit? And that's actually GNOME BFS daemon launching. The next thing I did is, why the hell does GNOME BFS daemon take such a long time to load? And well, I started going to GNOME BFS daemon, I fixed the problem, and now this has gone to, you know, being pretty much instantaneous. The same problem up there, you know, let me see if this works. So we have the same problem up here. Register icons. So Nautilus used to have, from the days of GNOME 1.4, Nautilus used to have this little function that initializes all the icons that Nautilus will ever use. So it reads a ton of files. It reads a big ton of files. Later in GNOME 2. Something very recent, we added this new way to GNOME to do all the icon registration and initialization, and it's really fast. So it turns out that Nautilus no longer needed that really old way to load icons, but nobody knew because that code was really old. Nobody had ever measured the timings, and nobody really remembered that it was there. So when we looked at this profile, we saw, oh, why the hell is it registering the icons? It doesn't need to do that anymore. So we just removed that function and removed the one line call to that function. And those, what, 1, 2, like 2.2 seconds, they just went away. Right? So if you spend a little time making a little automatic tool to draw this kind of profiling charts for you, you will have much easier time. I ended up getting like 30 of these charts, and they were just, you know, you could just look at them and immediately see that problem instead of going through this crap. Yes?
One question, how do you specify the logging points? Where you log?
Good question. The thing I did, so the only thing that S-trace prints is syscalls. So different points in the program, I wrote this little function that is, it's called the access system call. And to access, you pass a string. It's actually meant to say you have permissions to see a file. But instead of passing a file name, to access, I just pass this string, which is, you could do that with some cheaper hooks to actually get this, but it's much easier to just start with my hand in different points. So I just call access a bunch of times. Every single one of those calls fails. But then my little Python program looks for those failed access calls and it prints those. So if you take the time to write those little tools to see what's running a program, you'll have a much easier time getting it. I ended up getting like 30 of these charts, and they were really useful. So what do you do when you're profiling things? You have to take the same measurements over and over and over again. Especially when you're doing a lot of I/O, things get very unpredictable. The Linux kernel is a piece of shit when it comes to I/O, so it gives you really unpredictable results. So you have to run things many, many times, get some averages, do some statistics to get really meaningful results. Otherwise, one time you get a measurement of 4 seconds, the next time you get a measurement of 7 seconds, and it doesn't make any sense. So you have to take some statistics across a set of results. So you actually have to take the time to make that automatic, because if it takes you 2 minutes of typing things by hand to get one single set of measurements, you're going to do it twice, then you're going to be bored and go, look at porn or play Play or something. So you have to make it automatic. If it takes you 5 hours to write a little program to get those benchmarks, it's going to be much better in the end. So, what are the things you measure? You want to measure tasks. You want to measure fine-grained, well-defined tasks. We had a lot of trouble in Nautilus, and a lot of GUI programs have the same problem because they are very, very asynchronous. It's not like you want to measure the time from here to here in the source code, because that source code will set up idle handlers, and those idle handlers will set up timeouts, and those timeouts will launch threads, and the threads will later notify other threads when stuff happens, and you never have any idea of when that stuff finishes. So Nautilus does stuff like load the file list in an idle handler. Then in the idle handler, it loads the icon for a file, but that's also asynchronous, and it repaints the whole screen when it's idle, so you never know when that shit is finished. So what do? Well, you have to somehow insert a checkpoint when you're done. For example, in your repaint function there, you could check your pending your pending list of things to do, to say, do I have any other files pending loading their icons? Do I have any other icons pending scaling? Do I have any whatever? So, and not emit the checkpoint until all those conditions are met. So what are the problems that programs have? If you have never profiled an application, if you have just been adding code to it all the time, it's very likely that the problem is that your application is doing too much work. For example, a few months ago, gedit, the simple nice text editor for GNOME, it had this problem where gedit had this problem where you use the search and replace function and it was really, really slow. If you loaded a document with 20 pages and you hit search and replace, it would take a few seconds to go through it. And that's really slow. I mean, it's just scanning text. What's the problem with that? When we ran a profiler, we saw the following thing. We saw that gedit, search and replace, it was doing search next. And this guy, while more matches are available, search next, replace. Right? Very simple. But the gedit author did not know that this guy, search next, was doing, search for the text, search for the text to change a widget. And this change a widget was doing, it did search for the text, fine, very fast. For changing a widget, it was changing the sensitivity of the menu item that you used to search for the next item, so that it could show you whether there were any more items to search for by disabling the menu item, you know? And of course, change widget flipped a bit in one of the widgets, and then it is renamed. So every single occurrence of the text that you were searching for, it was causing a full repaint of all the menus. So the solution is to make the search function return whether there are actually any other items. You collect that information here, and only in the very end do you update the widgets, right? Did everybody understand that? Yes, no, I said? Okay. So it was doing way too much work for a simple operation. If you have never profiled the program, the next thing you'll notice in your application, it's probably that it's doing too much I/O. Once you have removed all the excess work, once you have gotten rid of all the crap, then you'll actually start to see real problems, like too much I/O, then bad algorithms, then smaller stuff like that happens with memory access, so we trash the cache. And until the end, you get to see really tiny things like, oh, you know, you should be using better instructions or other compiler options, but that never matters in the beginning because we're doing way too much stuff anyway. Some examples of bugs we have found. Bugs that are still present, and we have not fixed them. You know, so if anyone wants to fix those, feel free. So, how do you actually go about profiling? You have to characterize the problem. You have to say, okay, my problem is that this pop-up menu takes half a second to appear. From the time I click the mouse until it appears on the screen, it takes half a second, and that's way too much. Then you make a hypothesis. You say, okay, well, you make your hypothesis by asking the profiler, not by intuition, you know, because we are not magicians. So you ask the profiler and you say, oh, okay, the problem is that to create this menu, I have to load these 10 icons. Your hypothesis is if I didn't load these icons, it would be, you know, 10 times faster. Then you confirm your hypothesis. For example, you say, okay, I'm going to remove all that crap to load the icons, and I'm going to see how much time it takes to see if my theory was right. If it's really faster, then you found the problem. You just have to fix it. You have to change one thing at a time. That's the control panel of the Mark I computer, the first, the first computer. It's in Harvard University. So you have to restrain yourself from changing many little things at the time. Oh, I'm going to remove this code and move this one while I'm optimizing. No, you have to change one thing at a time. Then you confirm it, fix it, test it. Did you reach your goal? Are you done optimizing yet or not? So why do our disasters happen? Why is our performance so horribly bad? So programming is like building a sandcastle, you know? Programming is very funny because you can take like a pyramid and start by building a little tiny surface, and you pile stuff on top of it, and you have like an inverted pyramid, and computers let you, hold it steady. That never happens in reality. In reality, people build bridges by putting two big pylons on the ground, and then they build the bridge. So programming makes it very easy to hang things out of thin air. So we keep adding and adding and adding code to our programs. Then the sea comes along, and what happens to the sandcastle? It collapses. So how do we fix that? Well, we keep adding sand. That's not going to work. The next time a wave comes along, the whole castle is going to go to hell. So we have to do more engineering instead of piling code on top of things. We actually have to go measure things, establish our performance goals, fix things to reach those goals, and then have an infrastructure to make sure that those goals don't not fall to pieces. We have to have the benchmarks. We have to run them frequently. And whenever they start going more slowly than we intended, we know that there's a problem. During the last WADIC, we discovered that someone changed the caching scheme in FontConfig to cache the render glyphs. And before it used to be that most languages were, about equally fast or equally slow. But after they changed the caching scheme, everything is okay except Japanese, Chinese, and Korean. Those got 300 times slower. Why did nobody notice? Well, because nobody had run the profiles. I'm sure someone in China was really happy about that. So, for example, in GNOME, in 1997, our scheme to load icons was really simple. Our load icon function took an icon name, it built a file name just by pretending, user share icons, whatever, name.png, load the image, done. It was really, really simple. Then afterwards, the artists started going crazy and they wanted configurable icon paths and a bunch of crap. So now our icon loading thing looks like this. File names can have different extensions. And we can have many, many paths for the icons, right? So for each possible extension and each possible path, we look for it. If we finally found it, then we say, oh, is it an SVG? Okay, then load the SVG, scale it, and Kyrie is just so fast for that. So we load the SVG. Otherwise, we load the bitmap. After loading the bitmap, we scale it. Then we actually take the scaled image and add some cute shading to it to match the theme. That's just such a bunch of crap. I'm not kidding you. This is my GNOME icon path on my machine. This comes from the distro. The distro wants to be able to load icons from user-shared images, blah, 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 KD3, blah, 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 blah. KD is not even installed on my machine. I don't know where the hell those things came from. Finally, the GNOME ones, and every time my machine has to look for an icon, it has to go through all those paths. Why the hell did we make it so complicated? So, why do disasters happen? People just start writing a program and call our beautiful APIs. And to people, an API is like a flower. A pretty little flower in a pot. People see that flower and they see load icon. You cannot see it actually there because it's, too low resolution. But that flower pot actually says load icon on it. People don't know what's going on under that load icon function. If we look closer, if we look under the earth there's a big monster. People don't know what the hell is going on inside our pretty functions that we give them to use. They don't know that the monster here is going to bite their ass. They don't know that the monster wants to scan 1 million paths for 1 million extensions and it's going to load SVG files and render them and scale them and shape them. People just don't know that. So, how do we prevent that? What if our documentation said things like this? This is the function we use to take the hash. We use to compute the hash code for a string. It's really fast. It just goes through each character in the string once. What if we said, okay, this function is really fast. Its running time is proportional to the length of the string, and it will run really quickly. However, the performance of load icon is completely unpredictable because it could go to 1,000 paths, build the images, get a clever program to get the images for you, That would help, because if people read the documentation, oh, that's a problem. Okay. What if we made these annotations machine readable? For example, what if we put some dirty little XML in front of each function declaration, then have a program read those? So this is like the header files installed in your system. Then you're writing your own, this is your own code that you're writing in your text editor. This is your paint an icon, which name, you compute the area to draw, then you load the icon, then you paint the image in that area. If we had machine-readable annotations, then your friendly text editor could highlight that code and say, okay, you wanted to write a fast function here, but that's not going to work because you're calling a really slow function here. This is not my idea. This is an idea from one of the performance experts at Microsoft. They are actually adding these kind of annotations to all their .NET libraries, and they are going to make Visual Studio do that kind of stuff. So we have to catch up. again. Right? That would be a really cute hack. That's all for now. Yes?
What about any tools to help detect...
Whoa. Say that again.
What about any tools to help detect frequency of page faults and that kind of thing?
Oh man. So I asked the tech, well, Michael Mix did ask exactly that to Andrew Morton yesterday. That would be really lovely. We need a way to know, the question was, what about tools to detect things like page faults, which you cannot really control. I mean, you can control when you load a file, but you cannot control when your program does a page fault and the kernel has to go to this to fetch your data. I'd love to have those kinds of tools. For example, we have the problem where you're using your machine for a while, then Mozilla goes and eats all your memory and everything else gets spaced out, but you never know what happened there. Why is my program slow again? Well, it's Mozilla's fault, but anyways. So yeah, we need a way to know, this is the code that got paged out. Why is the next, okay, you saw how I was running OpenOffice right now? And I bet you that accessing my menu here is going to be really slow, even though I just used it, before I suspended my machine. I just clicked on it, boom. It took, what, like a second? The next time, it's really fast. What happened? It got paged out. But there's no way to know that currently. So we need hooks in the kernel to be able to tell us, these are the VMAs that got paged out. Those VMAs correspond to these libraries. Then once you know the addresses within those libraries, you can see, oh, okay, it's GTK paint menu that got paged out. Or it's all the icons you had in memory that got paged out. Yeah, we'd love to have those tools. Yes?
So that's part of the problem with having tools to find the problem. Another part of the problem is to have to find out how to get people to see what I still said that few people to understand the program started. No one seems to be interested. I mean, you keep blogging about them, but no one actually fixes their own application. Because it's not application. So how to tackle this problem?
How to tackle the problem of people not being interested in fixing their own stuff.
There are things you need to fix, but there are, like you said, hundreds of things static and going started. Then having extra libraries that directly linked to applications which take UID API changes from non-API accounts to stick there. There's not that interesting as finding between our debugs or whatever.
Well, actually, doing profiling is a lot of fun. So it's a lot of fun, but it's a kind of fun that takes, it takes some getting used to because the tools we have are really bad. And when you don't have the right tools, it's just too cumbersome to get started, To add access system calls and then get your logs and do it by hand, that's a pain in the butt. So someone needs to write better tools, and someone really needs to know what kinds of tools we need,
These tools are good enough and some few problems which are still classification. Like that hundreds of tests of anyone else but there's no way to know what it is.
I don't know why people don't go about fixing them. I mean, maybe we don't complain enough when speed disasters happen. Maybe we just assume, something must have gone wrong. Someone will fix it, but nobody does. However, I'm pretty sure people will fix things if they corrupted their data. Maybe they don't care as much as speed. Maybe they have to refocus themselves and say, okay, this program is really not fucking usable. It's this slow, so we actually have to fix it. No, everything is just as slow for them as for everyone else. In GNOME it took a while to get used to the idea that we have to make things usable. The people at Sun Microsystems banked on that same idea for a couple of years before everyone else got convinced of it. So maybe we just have to beat them in the head for a couple more years before they start going optimizing things. I don't know. I really don't. Anyone else? Yes?
Do you really think such a metadata principle is the way to go? The last thing you showed, because always somebody can't properly assess the speeds. Because you need to have a lot of correct information everywhere, otherwise the system breaks down. So if you if you have a large group and some of the people are not able, I think it would be better spent, for instance, in defining the thing you did with access, automatically placing synchronization points, logging points, to be able to profile.
Yeah, well, I mean, this is a preventive measure, not a corrective measure. So if this could keep us from doing some disasters, that would be good. Yes?
How does it with asynchronous stuff? I mean, you call the function.
Oh, with that you're totally screwed. With that you're totally
The function
screwed.
always comes back pretty quick.
Yeah.
After it sets something eventually take a whole lot of CPU time.
Yeah, I think one pattern we need to start using more is, you know, often you queue things in idle handlers, so put them in an async thread or whatever, but there's no easy way to know when everything is done. For example, in GTK, a lot of the time we have like GTK do something and it does it in an idle handler, but there's no object signal emitter when that thing actually finishes. So if we look for those places and start adding, I don't know, G-object signals like operation finished, we have that in some parts of the file chooser. That would help, because then you could hook your logs to those notifications.
Well, it's the idle handler itself, so every time it calls one of the idle handler functions, it goes, right, this one put that one to run.
Sure, we could do that.
That would be simple point of all this place together, because there's a line.
Yeah.
The actual idle handlers.
Yeah, in general, you have to find those places and add some notification back to them. Yes?
Would it be doable to create a debug idle handler specifically for web purposes that would do what you're telling it to do just as you're calling it, instead of putting it when it goes back to the main?
Then you would need a thread, and the way the thread notifies you that it's done is by, you know, some synchronization primitive, and those usually happen in the idle loop anyways.
So you call it like synchronous, like for instance, when you load item 3, you're telling it to load something in the idle handler. How about just doing it right now in the special idle handler? Would that be debug?
Oh, that actually brings up a good point. I'm really sure that the diesel people, when they were writing Nautilus initially, every single time they ran into a performance problem, they said, oh, let's create another thread and do the operation there. That's just like shoving the trash under the rug, you know? That work needs to happen regardless of when you do it. But they just created another thread, put everything there, and said, okay, the user will not know. They actually do. I mean, the stupid window takes like 5 seconds to open. This is how long Nautilus takes to open a window. I'm going to open my folder here, click, click. Right? It's ridiculous. By contrast, Midnight Commander, instantaneous. Let me change folders here. I'm going to hit enter. Boom. You never notice. It was just loading. Boom, boom, boom. Right? It's really fast. Well, that's empty. You know, this has a bunch of crap in it. It's really fast. And it's completely synchronous. It only does a read there, stab every file, print them to the screen. It's done. It doesn't try to load icons. It doesn't try to do, you know, compute fancy fonts with the fonts fitting the screen. I mean, it's much simpler. It's a text-based application. But, you know, if you run Windows Explorer, you will see that it's a lot faster than any of the crap we have right now. They have actually done their homework optimizing things. So you do not fix a performance problem by putting the operations in a thread or in an idle handler. It's going to take the same time. It's just going to be synchronous, and your GUI is not going to respond while you're doing it. Yeah, it's a lot easier to measure when it's not asynchronous. But often it's hard to change because the rest of the program assumes that. So you actually have to take your timings. Yes, anyone else? Yes.
Did you try UProfile? UProfile is a kernel profiler, but the kernel-based profiler. Did you try to use it?
I tried using OProfile and I found it ridiculously hard to use. One thing about profiling is that you want to get started really quickly. So the thing about usability also applies here. You know, we actually need to do some usability work in our development tools. Why does no one use OProfile? Well, perhaps it's too hard to figure out. And all the GNOME people are really happy, well, like, a bunch of GNOME people are really happy using sysproc because you run it, you hit start, you run the program, you hit stop, and boom, you have usable results immediately. And OProfile, it's like, oh, what's the command line, what's the configuration file? No, that didn't work. Let me look for another option. You know, I'm sure it's really powerful, actually, to show you things like, you know, to collect a lot of statistics from the system. It's really powerful, but it's really hard to get going. Yes?
Did you try cold lead?
Cold brand, yeah. Yeah, it's really nice. It's really nice. But, you know, I mean, I haven't gone through all the software on my machine looking for performance problems, just some of them. And, you know. Anyone else? Okay, thanks for coming.